Okay, so in this video, what we're going to do is we're going to look at torque. And torque, again, we're relating linear values with rotational values. So one thing to note is that really to begin things to rotate, you're going to have to apply a force, right? And so forces cause changes in motion. So if an object begins to rotate, then something must have caused that change in its inertia. So when we apply a force to an object, causing it to rotate, we call it a torque, right? And so this is what is causing the rotation. So really think about the effectiveness that torque is, the effectiveness of torques or forces in causing rotation. Okay. Now, what happens is not every applied force does cause a torque. And we're going to look at, I know we haven't kind of officially defined what a torque is and what are factors of torques, but let's look at some examples, some kind of like real world, right? So torque is really focusing around, when you open a door. Okay. So think about this. If you look at these four situations, which one of these will produce the greatest torque? And think about your personal life when you did this, or if you've done this before, where was the easiest really to cause that door to open, right? And we're talking about easiest, right? So if you look at the first one, situation A, we're applying a force at the hinge. It's like if this is my hinge, right? I'm doing this. It's not going to rotate, right, if I apply, right? And so the hinge is our axis, right? And so if we're doing it right on the axis, well, guess what? It's not going to cause rotation, right? It's not, so there's gonna be no torque applied. Now, the other situation where there's no torque applied would be the choice D. So if this is my door, my pinky's my hinge, and I'm pushing on it this way, right? I'm not causing a rotation because I'm applying a force that actually would try to compress the door. So situation D would be no torque. So now you're looking at B and C, right? So B and C are similar in the sense that they do both have a force applied away from the axis of rotation and not parallel to our axis of rotation. Now, but which one's going to cause the greater torque? If you look at C, that would be like pushing here in the middle, right? So if my pinky again is my axis of rotation, if I push here, I can cause some rotation, but it's a little bit more difficult, okay? But if I push way out here on the edge, right, that's going to be an easy way for me to rotate. So choice B would have the greatest torque. Now, if you think about this, this is why door handles are placed where they are. I once stayed in a hotel in Boston where they put the doorknob right in the middle, and I wanted to leave. As the physics person in me wanted to leave, the family man in me did not want to leave because it was with my family. But the physics person said, I don't know if I want to keep having to exert that much force just to open your door, right? If I do it in the middle, why not put it way on the end? Okay. But again, this is the reason why door handles are located where they are, because the further you are away from the axis of rotation, the easier it is to cause that rotation. All right. So now let's officially define what torque is. So torque is directly proportional to two things, both the force applied and the force's distance from the axis of rotation. And on the door, the axis of rotation is is the hinge. Okay. Now, the distance the force applied is caused. We give it a special name. It's called the lever arm, and it is we abbreviate it R, or we give it the variable R. Okay, so technically it is a radius, but it's not a radius, right? So it would be the radius of the circle that is created where you apply that force, but we just call it R. Now, the equation to find torque is torque, which is the Greek letter tau, right? Is R, so lever arm times force times the sine of the angle, right? Now, what happens is if you're applying parallel, right? The sine of 0 is 0. So there would be the torque of 0, right? And the sine of 90, which means perpendicular, would be 1, right? And so here you would have a torque of 0. Here you have a torque of R times F. And so anywhere in between, right, 0 to 90 would cause torques, okay? Now, the sine part of the equation is because the force must be perpendicular, okay, to the axis of rotation. Again, we're looking at the axis of rotation. And so if I just kind of do a simple little diagram, so the lever arm is coming out from the, so this would be my R, this would be my F, right? So it's coming out from the axis of rotation. I'm pushing down and causing a rotation. Okay, now torque is a vector, right? So the way to think about this, again, now you see that R times linear, right? Anytime you have R times linear, right, we have a rotational component. So so torque is the rotational equivalence to force. Okay. Now the direction again will follow our rotational coordinate system. Counterclockwise will be positive, right? And clockwise will be negative. Again, when you think about this, think about clocks to us are backwards. Clocks to physicists work backwards, right? Because it goes in the negative direction. And again, I talked about it before. This is based on the unit circle. Okay. Now, one of the questions that you often see here is how do we get things to balance? The way to think about this is that your torques that cause positive um, or forces that cause positive torques must balance the torques that cause or the forces that cause negative torques. Okay, so here you have an object weighing 120 newtons set on a rigid beam of negligible mass at a distance of 3 meters from the pivot as shown. A vertical force is to be applied to the other end of the beam at a distance of 4 meters from the pivot. To keep the beam at rest and horizontal, what is the magnitude of the force required? And so, an easy way to do this problem, let me scroll up a little bit, is to simply say, okay, I know I have two torques being caused here. Okay. I have a torque on the left hand side and I have a torque caused on the right hand side. And what happens is this torque is going to cause it to be positive, right? Because if I took the other force off, it's going to cause it to rotate in the positive direction. And this torque would cause it would be a negative torque, okay? Because it's going to go down and to the left. Now, if I'm looking for that force, right, all I simply have to do is substitute it. Now, both of these forces are perpendicular. Now, if you think about it, what force is here? It's the weight of this object. Because sometimes they give you the mass, and you would need to say, okay, what force is causing that torque? So in this case, it would be the weight of the 120 Newton block that is causing the torque. And so I'm going to say lever arm left times force left equals lever arm right times force right. Okay, and I'm going to solve for FR. So FR is RL FL over R right. And now I can just plug in numbers. So I got 120 times 3 over 4. And that's 360 over 4, which is going to be 90 newtons. So I would need to apply 90 newtons to keep this in balance. Okay. And what we do is I don't we'll talk about it later when we talk about rotational dynamics, but we'll talk about conditions of static equilibrium. And this is one of the first conditions of static equilibrium is that your torques must be equal. Okay. So in the next video, we're going to start shifting our conversation to that dynamics aspect of rotation.